Welcome to BKW Physics. I'm Mr. McConley, and we're starting projectiles today. Really enjoyable topic. We were just, before the video came on, talking about pumpkin chunking, which is a show that comes on once a year near Thanksgiving time. We're near Thanksgiving time. So, anyway, projectiles. They're the objects that are launched through the air. I know that's not a technical Webster type definition, but it works for us. The trajectory is the path that the projectile will follow as it goes through the air, and that's very predictable in physics. So we're going to start with what I call case A. Now that's not a technical name, I kind of made that up. I have a case A and a case B just so you can keep them straight in your mind. So case A is if something is launched or thrown horizontally. That, for example, might be, hey, you're standing on the edge of a steep cliff, and nearby here we have Roman's nose. So you're standing on the edge of Roman's nose, and you throw something off Roman's nose, which will probably get you in trouble, by the way, so don't do it. But you throw something off Roman's nose, and it will travel the trajectory drawn right there. And it's a very predictable thing. So we can figure out times, distances, how high you are, just based on one or two pieces of information. But the key is here is that you're throwing it horizontally. So the angle here is 0 degrees. Okay? If you throw it up or you throw it down, that's case B. But if you throw it flat, that's case A. So let's get to the bottom of how you figure out some different things. Say you want to know how far distance horizontal. That's how far something went. And the reason I write horizontal with the H is because we're going to deal with things vertically and horizontally in this chapter. So this is horizontal, how far it went, which is also could be called the range. The DH, distance horizontal, is a simple thing. It's just the velocity times the time. And you'll recall that goes all the way back to the reference table equation that's written this way. Velocity is distance divided by time. Why am I able to use this equation? Because this equation so far this year has been very limited. The only reason I can use it is because once you let go of the object, say that's a rock, and this rock is going at 2 meters per second. When you let go of it, you go throw it like this. How fast will it be going right here? Forward. 2 meters per second. How fast will it be going right before it hits the ground? 2 meters per second. See, your velocity forward, your horizontal velocity, this is a constant. You better star that. That's important. It's going to go the same speed until it hits the ground from the time it leaves your hand, because there's nothing speeding it up or slowing it down. Now some of you will be real technical. You say, oh, wait, there's some air resistance, and it's actually going to slow down a little bit. Yeah, you're right. But in high school physics, we're just not crafty enough to deal with that yet. So we're just going to say, once you let go of it at 2 meters per second, it will continue to go forward at 2 meters per second until it hits the ground. It's a constant. This equation right here will help you find the range. If you want to know how high the cliff is, you have a question? Okay. You want to know the height of the cliff. That is distance in the vertical direction, up and down. And I'm going to bring back an old equation that you probably recall. Initial velocity times time plus 1/2 gravity times time squared. You remember that. The only thing I'm going to do to this, I'm going to slightly tweak it a little bit. I'm going to say, okay, it's dv, how high. The velocity we're talking about is the initial velocity, and since this is vertical, what direction are we talking about here? Vertical also. And then that raises the question, how fast is the object going vertically when you let go of it? No, when you first let go of it, not the acceleration, because you're totally right about the acceleration being 9.81 negative. But how fast is it going up and down when you let go? It's not. It's 0. So if this is 0, you know what happens to this whole term? It's gone. Now the rest of the stuff stays though, 1/2 gt squared. So actually this equation, for the purposes of finding how high a cliff is going to just be 1/2 gt squared. So So if you know the time, you always know gravity. If you know the time, you can say, oh, it fell for 2 seconds, 2 squared times gravity divided by 2. Done. You know how high the cliff is. It's that easy. So let's do a quick example of this. Actually, what am I at for time right now? Okay, that's fine. I'll keep going. So, quick example of this. If I just get all mad at somebody, and I'm like, oh, crazy, because you're driving me crazy in class, and I take your physics folder, and I just whip it out the window, open the window, and throw it, I probably wouldn't do that. But if I did, this example might happen. So Joe here is irritating me. And I throw his binder out the window at a speed of 20 meters per second. I'm really angry. That's fast speed. And we note, because Frank, in the front row, pulls out his handy-dandy stopwatch and times it, and notices that it takes a time of 3 seconds to hit the ground. This could happen. Alright, so we know that it left at a speed of 20, is in the air for 3 seconds. Let's find some stuff out. First of all, A, let's make a table that shows the distance vertical, in other words, how high the binder is on the way down. The distance horizontal, how far forward the binder has traveled, all compared to the time. And let's just do it for the first 3 seconds. So time 1, time 2, time 3. So time, seconds, 1, 2, 3. And I think you can probably do this in your head, but let's just kind of, do the first one out. So if we want to know how far it's gone, the DH, we're just going to take the velocity in the horizontal direction times the time. How fast is it going when I let go? 20. How much time has passed after 1 second? 1 second. So, okay. It goes 20 meters. That's a long way. Okay. What's 2 seconds to be? 40 and 3. Okay. So we got 20, 40, 60. Let's do the same thing to figure out how high off the ground we are. So we do 1/2 gt squared. So this is actually telling us how far the thing falls. So we're going to do negative 9.81 meters per second squared, and we're going to say the time is 1 second, we're going to square it. So when we do this, it comes out to be a negative because of gravity. And the first one comes out to be somewhere around 4.9 meters. That's how far it's going to fall in the first second. I want to point out something to you. Does it matter if I threw a binder or a rock or a marker out the window? They would all fall 4.9 meters in the first second of falling. So in 1 Mississippi, it's going to fall about 5 meters. All right? If we do the same calculation again, we're going to get a negative 19.6, and then we're going to get a negative 44.1. So you can see after doing this problem that my example is totally unrealistic, because that would mean the building would be like 44 meters high, 44 times 3, it's like 120 feet high. We're not that high in the air. Okay, but just for example's sake, this is, if this situation, if this data was true, that's how high you are, and that's how far it flies. I'm going to do one more thing before we close up here. If I want to plot this, then I want to plot the distance vertical, and I want to plot on the other axis the distance horizontal. How might I do that? Well, actually I'm going to move my axis up a little bit. I need more space. So I'm going to move my distance horizontal up a little bit. Since they're all negative numbers, I can do something like this, like, 5, 10, 15, that's not big enough, I'm getting up to 40. Let's do it 10, 20, 30, 40, and 50 down here. Those are all negatives. So during our first second, how far have we gone? Well, here we go, up to 20, 30, 60. So we've gone 20 meters, and what height are we at? Right about there. After 40, or when we go 40 meters forward, we're at basically right there. And at 60 meters forward, we're way down here. Notice, that's the flight of the object I threw out the window. And that's the same path that's always going to be true. When you throw something horizontally, it's always going to follow the trajectory of being a parabolic or half a parabola on the way down. So for today, case A, physics.